based on the drug delivery to the brain parenchyma, based on the receptor-mediated transcytosis. As you know, all the time the drug delivery to the brain parenchyma is one of the most challenging one because of the blood-brain barrier that's really restricts the availability to the functional part of the brain, which is now the BBB. If you look at some acute and the chronic disorders which we can find in the brain side, the Parkinson, the stroke, the Alzheimer, infectious disease, and the tumor, which just comes from the glial cell and known as a glioblastoma multiforme, all of this disease is going to be the hard-treating disease. But what's the problem? Is the medicines, is the physicians or the pharmacists don't know how these disorders come from? What is the biochemical pathway? Thus, we don't have any suitable medication for treating such a disease. These are not the issue. The issue is there is a barrier, like the blood-brain barrier, that's really limitation the accessibility of the medicine to the functional part of the brain, which is now not the brain parenchyma. It means that the blood-brain barrier just limited, just allowed to penetrability of some material which is essential to the survivability of the brain, like the glucose, the oxygen, and some acid amines. And our drugs, as an external material, won't be penetrated because of this barrier. But the drug delivery to accessibility in the brain, if we look at it from the cellular anatomy to the blood-brain barrier, we can divide all the pathways into the two parts, the paracellular and the transcellular pathways. Paracellular pathways, because of the protein trafficking in the three parts, the desmosome, the antigen junction, the tight junction, is not really eye-catching one because the researchers need to do some manipulation on the structure of these proteins, the occludins and the jam proteins and so on. If we want to drug delivery to the brain by the paracellular, we need to manipulation the protein and it's threatening the integrity of the blood-brain barrier. That is not acceptable. But because of this reality, most of the researchers focus on transcellular pathways if we want to speak about them, we can speak about the RMT, which stands for the receptor-mediated transcytosis, AMT pathway, as stands for the absorptive-mediated transcytosis, CMT pathway, which is now the Trojan horse strategy, is based on the immune cells of the immune system of the body. At this pathway, the immune cells are targeted to the drug delivery to the brain parenchyma. And the transporting proteins like the glutamate for the transporting of glucose, this can be a need for the drug delivery. And the efflux form like the PG proteins and ATP binding acids. I mean that we can do some drug delivery by co-administrations of some inhibitors with our drugs. But it's not really acceptable because it's threatening the homeostasis of the brain. And the last one is the diffusion, which is works on the gradients of the substrate and the laminin and the basilateral side of the blood-brain barrier. Because of the importance, I'm just going to speak about the transcellular pathways. At the first, we had the cell-mediated transcytosis, as I speak before. It is now the Trojan horse strategy. In this method, we force our drugs to enter to the immune cell. It means that how we can formulate our drugs. There are some elements like their size. If we want to, it sheets from the immune cells, its size should be lower than something like 15 nanometer. But we use from this pathway, there's no exceptions. The reality completely turn over. We should formulate our nanocarrier or nanoparticle over than 100 nanometer. It means that this is the way that we can make that our drugs or nanoparticle as drugs or nanoparticle as drug carrier should be dedicated by the immune cell like the monocyte and the macrophage and phagocytes. And because of this kind of the cell ability in crossing the blood-brain barrier, our drugs can cross the blood-brain barrier. And it comes from the fact that the microglia, as the immune cells of the brain, is differentiated from the monocyte and the macrophages. At the second step, we had the TG-mediated transites, which is known as not eye-catching one, because the side effects in this method is so high and it's unacceptable. One of the aims of the drug delivery is limiting the doses of the administrated dose of the drugs, and also the diminishing the side effects of the drug. So this method is based on the electrostatically interactions of our nanocarriers and with our tissue. As you know, the phospholipid bilayer membrane of the cells is negatively charged, so our nanodrug carrier should be positively charged. For this, for catching to such an aim, we can use from the CPP protein, which is like the symmetry. We know them CPP. We coated the nanocarrier with this kind of the proteins, and the interactions that took place between the positively charged and the negatively charged of the phospholipid can be our drug delivery. But it's not acceptable, because the phospholipid membrane is not just for the blood-brain barrier. We can find it in the old cells, on the old parts of our bodies, and the side effects will be high. But the best way, which most of the researchers over the time is going to be in this part, is the RMT pathway, which is so specific. If we study our pathology condition and the AM tissue, it will be the really work. The other way is going to be the protein carrier pathways, like the GLUT, as the carrier ways for the glucose. It's going to be the suitable one, because in the drug delivery the priority is don't treat the integrity of the blood-brain barrier, and don't threaten the first priority of the brain, which is the survivability. The glucose is needed for the neurons and the neuron cells. If you use from this pathway to drug delivery, we have a competition between the drug and the glucose to enter into the brain. And it's not a suitable thing, because the survivability, the nutrient, is the first priority, and the drug delivery will be the second priority. Inhibition of the efflux pump, there are some researchers that work on it. As you know, the efflux pumps efflux any external material which can penetrate to the ball, our tissue, as our drugs. Our drugs can be an external wall, so the efflux pump works really against it. But with the co-administrations, some inhibitors which really inhibit the efflux pumps in the short time. I emphasize in the short time, because in the long time it's really it's not be acceptable. This is so essential for the hemostasis of the brain. Here I have an example. Proronate P85 is one of the inhibitors of the efflux pump, like the PGP or multi-drug resistant proteins. It's co-administrated with the drugs, and the drug delivery efficacy, the growth. As I said before, the paracellular routes, which is based on the manipulation of the structural proteins, is not going to be some suitable one, because the proteins should be manipulated, and it's really threatening the integrity of the blood-brain barrier, and it's threatening the hemostasis of the blood-brain barrier. As the receptor mediated to the brain drug delivery, what is the advantage? The advantage is that this method we have the side effects very low. We formulate our drugs to one specific receptor. For example, we have types of the receptor which are expressed on the luminal side of the blood-brain barrier, like the transferrin. We can use from the transferrin as a ligand on the surface of our nanocarrier, or the nanoparticle as the drugs, and the interaction just took place between the transferrin as the ligand and the transferrin receptor on the blood-brain barrier. Here are some examples for the RMT pathways which can be considered, like the insulin receptor, the transferrin receptor, the LRP1 and 2, and the diphtheroatoxin receptor. These are some examples between this receptor. The transferrin receptor was more considerable in the researchers because this is one of the high expressed receptors in the blood-brain barrier rather than the LRP or insulin receptor. And another most important reason is that the transferrin receptor expression under pathological condition really change. In some pathological, it's overexpressed. In some other pathological condition, down regulate, and it can be considerable in drug delivery, and it can be a nice target. Another most important issue is the selection of the receptor, which is based on this reality. We should know our bumps and the pathological conditions very well. And based on this, we can choose our suitable receptor. Another important issue that should be considered in receptor-mediated drug delivery to the brain parenchyma is the ligand density on the nanocarrier. Before 2015, it was a really challenging one. If your ligand density on the nanocarrier will be low, the interaction won't be nice. Won't be in a level that the transportation of the drugs took place. But on the other hand, if the density of the ligand on your nanocarriers will be high, a phenomenon will take place which is known as the avidity. I don't like to speak physiologically about this pathway, but as you know, after that interaction between the ligand and the receptor took place, the vesiculation took place, the vesicle and the endosome, and it comes to the cytoplasm. And based on acidification, the dissociation between the ligand and the receptor took place, and just our nanocarrier released to the brain parenchyma. But when our density of the ligand on the nanocarrier is high, what's the phenomenon? Phenomenon is avidity. It means that the interaction is not just between one ligand and one receptor. In avidity, we have interactions between, for example, more than one interaction. In avidity, we speak about more than one interaction. For example, in avidity, we have 4 interactions, 4 ligands, 4 interactions, 4 ligands with the 4 receptor. In this case, when the vesiculation takes place, the acidification cannot dissociate this, for example, for linkage. For example, it can linkage 1, 2, but it's not worth all of them. So the dissociation won't place and the drug delivery won't be acceptable. Before 2015, it was a challenging issue. But after 2015, based on the research which published on the PNAS journal, the solution, the problem solved by adding acid-sensitive linkage between the ligand and the receptor. For example, diaminoketal. If you add such a linker between your ligand and the non-particle core, any little diminishing in the pH in your endosome is enough for dissociations, all the linkage in the avidity phenomenon. So after 2015, we had solved it. I'm the master student of the biotechnology in Iran. We're working on the brain drug delivery based on the receptor. This was the an overview from our ongoing projects, my master thesis. And I hope that our data will be prepared for the next PDDS in Paris in 2019. This is my advisor, the pharmacist, and the first supervisor, microbiologist, the second supervisor, a nanotechnologist, and me as the operator of this research. Thank you for your attention.
Okay, any questions for speaker?
So, what's the concentration of uronic P85 to inhibit efflux pump?
Yes. When we add the efflux pump in our drug delivery, this efflux pumps should be, if we inhibit this efflux pump, the drug delivery will be more successful. So we need some chemical things to really inhibit this efflux pump. The pluronic acid, or the P85, one of these inhibitors that should be co-administered with our drugs. I mean that in formulations of our drugs, it will be in the reactions. It will be in our drugs in formulation or as a ligand beside our target ligands on the surface of the ligand. When it's circulated in our bloodstream, and it contracts with our ligand, it contracts with the efflux form and interlines with the cytoplasm part of the cell. When the efflux bonds comes to show their act, anaphylaxis gradient, anaphylaxis material, our inhibitor work and deactivate it, but for short limited of time.
Yes, for that short, how short it is?
What do you mean
For
from?
you said, for example, for the inhibition, it lasts for how long?
It means that I'm speaking about the concentrations.
Okay.
If you don't manage the concentrations, if the concentration of the inhibitor in the bloodstream, or the concentration of the inhibitor in your formulation of the nanocarrier or nanoparticle will be high, it will be, its effect on the efflux form will be high. For example, I said that the inhibition of the efflux form will be when the concentration is high, the efflux form inhibition will be the high. And it's not acceptable because these are the physiology, these are the working for the homeostasis of the brain for a limited time. For a short time, we inhibited in our formulation, and the problem solved.
Any more comments? Or anybody would like to say something?